Welcome, intensely curious technical minds, to AI Paper Podcasts.
Great to be here.
This is where we distill the latest AI and tech papers, transforming complex concepts into clear, actionable insights. Basically, giving you a serious shortcut to staying at the forefront of research. And today, we're embarking on a fascinating deep dive into a paper that tackles, well, one of the most frustrating challenges in building truly intelligent AI agents. How to make them reason coherently and efficiently, not just stumble their way to a final goal.
Exactly. This deep dive centers on the paper RLVMR Reinforcement Learning with Verifiable Meta-Reasoning Rewards for Robust Long-Horizon Agents by Zijing Zhang and colleagues from Hunyun AI Digital Human at Tencent.
Right.
For those of you working with large language models, autonomous agents, especially on complex multi-step tasks, well, this paper introduces a pretty significant leap forward.
Okay, so for our short-form digest, let's try and unpack the core problem, their ingenious solution, and the results all within, say, the next minute or so.
Okay, sounds good. The fundamental problem RLVMR addresses is that traditional reinforcement learning for these long-horizon AI agents, it often optimizes only for final tasks.
Well, getting the answer right, basically.
Right, and this leads to what they call inefficient exploration. Imagine an agent getting the right answer, but by sort of blindly flailing around rather than truly understanding or planning its steps.
Yeah, makes sense.
It's brittle, struggles to generalize.
Right, and the solution they propose is RLVMR, a novel framework introducing verifiable meta-reasoning rewards. So it teaches agents to, think about thinking by explicitly tagging and rewarding cognitive steps like planning, exploration, reflection during the task.
Precisely. It's not just about the destination, but the quality of the journey, you could say.
Okay.
And the mechanism behind this involves combining traditional outcome rewards with these dense, programmatic, rule-based rewards for good reasoning behaviors. The training itself is quite clever, split into two phases. A small, cold start, supervised fine-tuning, then the main reinforcement learning phase.
And the results? I hear they were pretty impressive.
Yeah, quite. RLVMR achieves new state-of-the-art performance on challenging benchmarks like ALFWorld and ScienceWorld. It drastically cuts down repetitive and invalid actions, leading to significantly improved generalization.
Okay.
And what's truly groundbreaking here, I think, is that even smaller RLVMR trained models can actually outperform much larger, more powerful models. It proves that smarter reasoning can trump sheer scale, at least in these kinds of complex tasks.
Wow. So for you, the practitioner or researcher listening, this means we're looking at agents that are not just more successful, but also more robust, efficient, and crucially more interpretable.
Exactly.
Now, let's go deeper into how they actually achieve this. Let's start with this idea of inefficient exploration. We've all seen AI agents that seem to wander or repeat themselves, right? Even if they eventually get the task done. What's the fundamental trade-off these researchers are really getting at here?
Well, it raises a critical question. Are agents truly reasoning, or are they just finding these brittle shortcuts? The paper highlights two dominant training paradigms that really expose this trade-off.
Okay.
First, you've got supervised fine-tuning, or SFT. This approach is good for teaching efficient, specific behaviors, but it's often brittle. It struggles to generalize to novel situations.
Right, like it memorizes too much.
Sort of, yeah. For instance, a 7B model trained with SFT, its success rate plummeted from 63.3% on familiar tasks, they call that L0, to just 37.5% on completely unseen categories, L2.
Oh, yeah.
And its repetitive action rate nearly doubled when faced with novelty, jumping from about 14% up to nearly 25%.
Okay, so SFT is efficient but brittle. Then on the other side, you mentioned reinforcement learning with outcome-only rewards like GRPO. How do they stack up?
Well, RL, particularly GRPO, does encourage exploration and it gets better generalization.
Yeah.
The GRPO 7B model, for example, achieves significantly better generalization, 77.3% on L1, which is unseen object combos, and 52.3% on L2.
That sounds better.
It is, but it often reinforces flawed reasoning, even if it ultimately leads to success. That same 7B GRPO model had a staggering 31.2% repetitive action rate on those difficult L2 tasks.
31%, wow.
Yeah, so you get success, but it comes at the cost of this highly inefficient, almost blind exploration. The agent is kind of flailing its way to the goal.
Okay, to really get a handle on this inefficient exploration, could you walk us through an example, maybe that one from the paper about putting keychains in a safe? How does that actually look?
Absolutely. So imagine a GRPO trained agent trying to do exactly that.
Yeah.
Put two keychains in a safe. By step 7, it's already at dresser 1, where the keychains are. It successfully picks up the first one. So far, so good.
Okay.
But then, for the next few steps, steps 8, 9, 10, its internal reasoning output literally says, I need to find another keychain. But its action is repeatedly go to dresser 1.
Even though it's already there.
Even though it's already there, it's just wasting steps. It demonstrates this fundamental lack of self-awareness in its reasoning process.
Yeah.
It's not reflecting on its current state effectively.
Yeah.
Probably overfitting to training data, not really understanding the environment.
Right. And they found that just throwing more compute at it, like scaling up the model size from, say, 1.5 billion parameters to 7 billion, that doesn't fix this underlying problem, correct? My gut feeling would be a bigger model should be smarter.
That's the common intuition, yeah. But the data here is really striking. The 7B GRPO model, despite having higher overall success rates, actually showed a higher repetitive action rate.
Higher?
Yes, 31.2% compared to 27.1% for the smaller 1.5B model.
Wow.
It's a critical insight. Larger models might just be more effective at exploiting these flawed, inefficient strategies rather than developing genuinely robust reasoning. It tells us the problem is really in the training objective, not just the model's capacity.
So scaling isn't the magic bullet here.
Not for this problem, no.
Okay, so if that's the core issue, what was the clever idea these researchers came up with? How did they tackle this inefficient exploration directly?
Well, RLVMR, their solution, draws direct inspiration from metacognitive theory. You know, the idea of thinking about thinking.
Right.
The core insight is that high-level cognitive skills, things like planning, monitoring, exploration, reflection thing, these can be explicitly rewarded, and therefore learned by the agent.
Ah, okay. So instead of just the final, good job, you got the keychain, they're actively rewarding how the agent thinks about getting it. How do they actually operationalize that, like in the model's output?
Yeah, what's really fascinating is how they extend the popular React framework. React usually just alternates think and act. Simple enough.
Right.
RLVMR introduces specific meta-reasoning tags. They look almost like XML tags that the agent learns to output as part of its thought process. These tags mark out distinct cognitive functions. It gives the AI this kind of structured internal dialogue.
What kind of tags are we talking about?
So there's planning. This is for formulating an overall strategy, breaking tasks into high-level steps. Used at the start, or maybe if it needs to replan. Then explore. This one's for generating hypotheses or options when things are uncertain, maybe finding a new object or figuring out where to go next.
Makes sense.
Reflection. This signifies reviewing past actions, analyzing errors, figuring out corrective actions. Typically after something fails or it gets stuck, it's like the agent debugging itself on the fly.
Nice.
And finally, monitor. This is for tracking progress and making sure it's sticking to the plan during routine execution when things are going as expected.
Okay, these tags make the thinking process explicit. But how do they translate into actual rewards? It's not just one overall grade, right? It sounds more like grading different parts of the process.
Exactly. That's the key. They use a composite reward signal. You still have the sparse outcome reward that's just a binary signal, 1 or 0, for final task success. Did you do it or not?
The final grade.
The final grade, yeah. But then, crucially, there's a dense step-level meta-reasoning reward, which they call RMRT. This is the process-level feedback.
Okay, how does that work?
Well, for example, a planning step gets rewarded if the whole trajectory ultimately succeeds, rewarding good foresight. An exploration step gets rewarded if the action targets a new object or location, directly discouraging just wandering back to the same place.
Ah, smart.
A reflection step gets rewarded if it actually leads to a corrective action. After a failure, teaching the agent to learn from mistakes. And there's even a format reward penalty if the output doesn't follow the tag.action.action structure, keeping the internal dialogue coherent.
Like rewarding good note-taking.
Kind of, yeah. It ensures the structure is maintained.
That's a brilliant way to supervise the thinking itself. Okay, so how do they actually train an agent with this complex reward setup?
The training involves 2 key phases. First, there's a brief cold start, supervised fine-tuning phase.
Cold start.
Yeah, they take a surprisingly small data set, only about 200 successful trajectories, and use a more powerful teacher model, like GPT-4, to annotate these trajectories with the meta-reasoning tags, basically inferring the likely cognitive step for each action.
Okay.
Then, they fine-tune the target LLM on this annotated data.
So it's like learning the grammar of good thinking first, learning what these tags even mean and how to use them.
Precisely. It bootstraps the agent's ability to generate this structured meta-reasoning. Then comes the main part, the reinforcement learning phase. They use a modified algorithm called Meta-Reasoning Group Policy Optimization, or GRPOMR.
GRPOMR. Right.
And instead of needing a separate critic model, which can be computationally heavy for LLMs, it computes advantages by comparing different trajectories starting from the same initial state. Much more practical for these big models.
And the real magic is how it combines the rewards, right? The overall outcome and this detailed meta-reasoning feedback. That's the secret sauce.
You've nailed it. GRPOMR calculates two types of advantages. First, a trajectory-level relative advantage. This captures the overall success, normalizing the final outcome reward across a batch. It's the big picture. Did you complete the task? And second, the meta-reasoning level relative advantage. This is where it gets granular. They group all steps within a batch that share the same meta-reasoning like all the Explore steps, and normalize the rewards within that specific group.
Ah, okay. So comparing apples to apples for each thinking style.
Exactly. It provides fine-grained, context-aware feedback for each type of cognitive behavior. Then these two advantages, trajectory level and meta-reasoning level, are weighted. They used a 50-50 split in the paper to form the final step-level advantage that drives the policy updates.
Wow.
A really clever way to balance global task success with that local process-level intelligence, creating the final answer and the thinking that got you there.
That's a powerful framework. So we've talked theory, but what actually happened when they put RLVMR to the test on benchmarks like ALFWorld and ScienceWorld? Did it deliver?
Oh, it delivered. The results are quite compelling. RLVMR consistently achieves new state-of-the-art performance across both benchmarks, all model sizes.
Really? Like what kind of numbers?
Okay, so for instance, with the Quinn 7B model on ALFWorld, RLVMR hit 91.4% success on the seen tasks, the L0 categories. Pretty good. But crucially, it achieved an impressive 83.6% on the hardest, totally unseen L2 task split.
83.6% on unseen. That's huge.
It is. That's a 16.4 percentage point jump over the strongest baseline they compared against, GPO. A massive improvement, especially where it counts on generalization.
That's incredible. Does this really mean that smaller models using RLVMR can actually outperform much larger sort of brute force models?
It absolutely does. And this, for me, is one of the most groundbreaking insights in the paper. Their Quinn 1.5B model, trained with RLVMR, achieved an 87.9% success rate on the unseen L1 split of ALFWorld.
Okay.
That decisively outperformed GPT-4, a vastly larger model, which only scored 66.0% using a standard prompting strategy on the same task.
Whoa. Okay, so the little guy wins with smarter training.
Exactly. It powerfully illustrates that this targeted process-level supervision through meta-reasoning rewards is potentially a more effective path to high performance than just relying on the sheer scale of massive pre-trained models. It suggests a different way forward, maybe.
So they're not just more successful, but also more efficient in how they explore. They really tackled that inefficient exploration problem.
Yes, and there's direct evidence for that. RLVMR drastically reduces those repetitive and invalid actions we talked about. For example, their 7B model's repetitive action rate on seen tasks, L0, just 2.3%.
2.3, compared to what for GRPO?
Compared to GRPO's 21.5%, so a nearly tenfold improvement.
Wow.
And its invalid action rate was more than halved too, dropping from 14.8% down to 5.6%. Much cleaner execution.
And does this efficiency hold up under pressure on those really tough unseen tasks where things usually fall apart?
Precisely. While GRPO's inefficiency actually got worse on unseen tasks, remember they jumped to 31.2% repetitive actions on L2? RLVMR's stayed controlled at a much lower 11.7%. It demonstrates a more robust and generalizable reasoning process. The agent isn't just recalling memorized solutions, it seems to actually understand how to navigate new situations more efficiently.
Can you give us another concrete example of this? Maybe that self-correction one with the soap bars? How does an RLVMR agent handle a mistake differently?
Certainly. Okay, consider an RLVMR agent trying to find two soap bars and put them in the cabinet.
Yeah.
At step 13, it's carrying one soap bar. It's actively exploring new locations. Good. But then it experiences a brief hallucination at step 14. It tries an ineffective action, like examine soap bar 2, even though soap bar 2 isn't actually there. A common failure mode.
Okay, so it messed up. What happens next?
Instead of getting stuck or repeating the error at step 15, it immediately triggers a reflection step. Its output says something like, wait, that didn't work. Let me double check my inventory.
It catches itself.
Exactly. It avoids getting stuck in that error loop.
Yeah.
It demonstrates genuine adaptive reasoning, learning from and correcting its mistakes in real time. That's a cornerstone of robust intelligence, right?
Absolutely. And I assume this also leads to shorter solution paths overall, because it's not wasting time looping or flailing.
Indeed. On that challenging unseen L2 split of ALFWorld, RLVMR agents needed only 15.4 actions on average. Compare that to GRPO's 21.7 actions.
That's like, what, almost 30% fewer actions?
Yeah, a 28.1% reduction. Much more direct, purposeful problem solving. And they also observed faster, more stable convergence during the RL training itself. These process-level rewards provide a clearer learning signal, preventing the agent from developing those bad, loopy habits in the first place.
Okay, so the benefits are clear, but to really understand why it works so well, they did an ablation study, right?
Right.
Where they removed key components to see what breaks. What did they find?
Yeah, those ablation studies are always revealing. And this one really highlights this framework's synergistic design. It shows it's not just one thing, but the combination.
So what happened when they took parts away?
Okay, first, removing the meta-reasoning reward. They call this WOA AMC. This caused a significant performance drop, 11 percentage points on ALFWorld L2, down from 56.3% to 45.3%.
So rewarding the thinking process itself is crucial.
Absolutely. It proves that directly rewarding how the agent reasons is vital for robust problem solving. Outcome-only rewards just can't do that alone. It directly hits that inefficient exploration issue.
Okay, what about removing the final outcome reward?
That was removing the outcome reward. Led to a catastrophic performance collapse. Success plummeted to just 12.5% on ALFWorld L2.
Wow, okay.
So, while meta-reasoning shapes how the agent thinks, that global signal of task success is absolutely essential to point the agent towards the actual goal. Without it, it might think nicely, but about useless things.
Need both the journey and the destination.
Precisely. And finally, removing the cold start phase, OCS. This also resulted in a substantial performance decrease. That brief low data SFT phase, remember, just 200 trajectories, is critical.
What?
It's needed for the model to even learn how to generate the meta-reasoning tags syntactically. It prevents the policy from collapsing later during RL training, especially for the smaller models. It's like the essential groundwork.
So it really is the thoughtful combination of all these elements, the cold start, the dense meta-reasoning rewards, and the overarching outcome reward that makes RLVMR so effective. It's not just one magic bullet.
Exactly. This study is a great example of how in advanced AI, it's often not about finding one single trick. The real power lies in a carefully orchestrated synergy, where the parts work together to achieve something much greater than they could individually. It's about holistic system design.
Makes sense. It's about designing systems that are more than the sum of their parts.
You got it.
Okay, so to bring it all together then, RLVMR successfully tackles this really nagging problem of inefficient exploration in long-horizon agents. By integrating these dense, verifiable rewards for explicit meta-reasoning behaviors, it essentially coaches agents to be more robust, efficient, and adaptive, moving beyond just hitting the final goal to actually reasoning effectively about how to get there.
Yeah, this deep dive really underscores the importance of supervising the reasoning process itself. It's not just about what the agent does, but how it thinks about doing it. And we've seen how this approach leads to agents that hit new SOTA results, generalize way better to unseen tasks, make far fewer repetitive errors.
And even lets smaller models punch above their weight.
Right. It offers a scalable and effective method for building more reliable and generalizable autonomous agents. It really does set a new standard, I think, for performance in these complex long-horizon tasks.
And that leaves us with a really provocative thought to ponder. If rewarding these internal cognitive steps planning, reflection is so powerful in these text-based environments, what are the implications for building truly capable, truly trustworthy AI systems in much more complex real-world scenarios? You know, things like robotics or scientific discovery, maybe even software engineering. What new horizons could this kind of teaching AI to think about thinking approach actually unlock for the next generation of AI?
Yeah, that's the big question, isn't it?
Indeed. Well, you've just experienced another deep dive with AI Paper Podcasts. We hope you feel a little more well-informed and definitely a lot more curious. Until next time.